Hi everyone. My name is Hsieh. So I'm an assistant professor in UCLA Computer Science Department, and I'm very honored to get receive this Samsung AI Researcher of the Year award. So my research is mainly on um, robustness and efficiency of neural network. I graduated from UT Austin in 2015, and I stayed in UC Davis for 3 years, and then I moved to UCLA in 2018. Today I will mainly focus on my research in the scalability and tunability of neural network training. And if you are interested in my other research like robustness, then you can also contact me offline. Okay. So today I will first focus on the scalability of neural network training. On one hand, we have a lot of large-scale training tasks, like we want to train the model for ImageNet classification. We want to train the very large BERT NLP language modeling. So for those training cases, you have a lot of computational requirements. So the ImageNet training usually require like around 1,000 petaflops, and the BERT training is even much more expensive than this. On the right hand side, we have also many modern like high performance computing clusters. Like in the most recently MLPerf in 2020, Google built a computing cluster with 4,000 TPU v3. So in those kind of high performance computing cluster, you have a lot of petaflops you can achieve in the peak performance. For example, this one can do like 430 petaflops. So ideally, we can actually train machine learning models very efficiently. Like if we divide 1,000 by 430, we can train the ImageNet in 3 seconds. However, currently it's not impossible to do that. And today I will talk about the difficulty of doing that and how our proposed algorithm can partially solve the problem. Okay, so first let's get some review of the basic training algorithm for neural network. So stochastic gradient descent is one of the most widely used algorithms. Each iteration, they randomly sample a batch of training data B, and then compute the average gradient on the current batch. So we assume the average gradient on the current batch can be used as an estimation for the floor gradient. And then we use this gradient estimation G hat to update the model parameter. So in other advanced optimizers, usually you still do this process. The only difference is you change the final update rule here, like considering adaptive or other small modifications. So in those kind of stochastic optimizers, one important parameter is the batch size. So usually, if you have one GPU, then you want to choose the batch size to fully utilize your GPU computation power. So usually in ImageNet, you use 256 for one GPU. So we want to consider the scalability. So what if we have 100 GPU? A very simple but very effective way for scaling SGD to larger number of GPU is to do this data parallelism. So the idea is you have several 100 workers. So you ask each worker to compute the average gradient for 256 samples. So total, and then you do the all reduce to average all the gradients to get the final gradient estimation, and then use that to update your parameters. So in this case, if each worker handle 256 samples, then totally it's equivalent to a SGD algorithm with batch size 100 times larger than this. So we call this large batch synchronous SGD training. This sounds like very simple, but what's the difficulty for scaling this up? In practice, people found that if we do large batch SGD training, it actually leads to poor performance. So in this first example we show on SAIF 10, if you increase the batch size to 2,000, your accuracy actually decreased from 90% to 82%. So the same phenomenon can be observed on ImageNet training. So why is this the case? Why, when we increase the batch size, it will hurt the final converged solution? Empirically, people find that if you use large batch training, then usually you converge to sharp local minima, like the right-hand side in this figure. So if you converge to this very sharp local minima, and usually the testing distribution is slightly different from the training distribution, then because your solution is not very stable, so you encounter a very large generation error when you consider test data. In comparison, the test performance will be good if you converge to a flat minima. So why why do we converge to a sharp minimum when you use large batch? So in standard small batch SGD, because your gradient estimation is very noisy, so the noise actually help you to escape from sharp minimum and go to the flat minimum. But when you increase the batch size, because you don't have enough noise, you actually stuck in this sharp region. So one simple solution people commonly use is to try to keep the noise in the same level when you increase the batch size. So let's do some simple calculation. If you calculate the variance of the gradient estimation with batch size B, then you'll find the variance of this term is proportional to 1 over the batch size. So a simple idea is I multiply a learning rate in front of this gradient estimation. So if you have batch size 1 over B, then I can scale my learning rate linear to B. Then I can cancel out this effect and I get the same noisy level. So there are several rules proposed, like learning rate. You use the linear learning rate scaling or the square root learning rate scaling. But both of them are trying to increase your learning rate when you increase the batch size. However, there's a limitation for this kind of approach. So many tuning, for ImageNet, people can only scale to 8,000 batch size, but you cannot really recover the original performance for 16,000 batch size. And what's the reason of that? So in optimization, there's a fundamental limit on the batch size. In gradient descent, your learning rate has to be upper bounded by some constant called Lipschitz constant. If your batch size is larger than that, then your algorithm is going to diverge instead of converge. So what happens here is when you increase your learning rate too large, your algorithm is actually going beyond the learning rate's upper bound, and the algorithm cannot converge properly. So to study how to handle this problem, we look at the parameters of each layer. So for each layer of neural network, we try to compute the parameters, the ratio between the parameters and the gradient. So this can be used as the estimation of how much learning rate you can allow for each layer. So we can see there are some layers where you can allow a much larger learning rate, whereas for some layers, you cannot really increase your learning rate by a lot. So this non-uniformities actually creates a difficulty in training. So to make it easier to use larger learning rates, we propose a very simple modification to the current algorithm. In this is called the adaptive learning rate scaling for each layer. So for each layer, you try to scale your learning rate by the ratio between W and G. W is a parameter of that layer, and G is the gradient of that layer. So the update rule is very similar to original SGD. The only difference is you have a layer-wise learning rate scheduling. And actually, you can also generalize this algorithm to other optimizer like Eden. So for Eden, G will be the Eden update vector, and then you can do the similar learning rate scaling. With this modification, we can increase the large batch size to 32,000 without sacrificing accuracy, and even to 64,000, it only goes down for 2%. And with some data augmentation, actually, we can recover the original performance even under 64,000 batch size. So in the end of 2017, we used this algorithm to achieve like a ImageNet training within 20 minutes. And after that, there are many papers try to use the same algorithm and better hardware or better data augmentation to improve the performance. In the most recent work, Google and NVIDIA both use this large algorithm to achieve less than 1 minute training time for ImageNet. So we also try to apply this algorithm to BERT training. You can see the original BERT required 3 days training with batch size 512. Using our algorithm LAMP, which is the adaptive scaling version of Adam, we can increase the batch size to 32,000 or even 64,000. And the training time will reduce to a little bit more than 1 hour using 16 TPUs. And the most recent result by Google and NVIDIA, they also pushed this using the same LAMP algorithm to within 1 minute using a lot of GPU or a lot of TPU. So this is mainly about the scalability, assuming the best hyperparameters are known. So actually in this work, we try to claim we can train the model very efficient, but this is under the knowledge of the best hyperparameter. And this is still useful in some cases. For example, if you have in company, there are usually some tasks, a model you want to train periodically. So you kind of knowing the best hyperparameter already. And also there are many times you just need to slightly change your existing model. So you probably have a good idea where is the best parameter. However, in most of the typical case, actually a typical user may not know the best hyperparameter. And this is like a more general scenario for standard users. In that case, many existing work try to evaluate a optimizer by the performance efficiency under the best hyperparameter. But we argue this is actually the wrong way to evaluate the optimizer. To properly evaluate the how efficient you can use optimizer to solve a practical problem, you need to consider hyperparameter tuning time of the optimizer. So how do we develop an evaluation method to consider the hyperparameter tuning time of the optimizers? Let's first take a look at this simple example. So we have two optimizers, optimizer A and optimizer B. You can see optimizer A is more sensitive to hyperparameters, but it's getting better performance in the best hyperparameter. And if you evaluate the optimizer based on the best hyperparameter, you're going to think optimizer A is much better than optimizer B. And this is done in almost all the previous work. And every time when people propose a new algorithm, usually they try to evaluate on the best hyperparameters. And there's only one recent work try to think about how can we evaluate a hyperparameter tuning time when comparing optimizers. But in this work, they try to consider the random parameter search time. So if you consider random parameter search, you randomly try to choose some parameter and run it to the end. In this case, they will think optimizer B is much better than optimizer A because it's actually very hard for the random search to hit the best hyperparameters. So in practice, we think both of these approach are going to either overemphasize or underemphasize the importance of hyperparameters search. So in practice, when a user try the optimizer, they can usually skip the bad configuration very quickly. For example, if I try a very large learning rate and the algorithm diverge in few epochs, I can directly stop this configuration without running to the end. So you need to, when you consider the comparison between optimizers, you also need to see how easy can the user skip the bad hyperparameters. And for some so even though optimizer A have a lot of bad hyperparameters, maybe it's very easy for the user to terminate those configurations and find the best better configurations. So in our evaluation, we try to show using hyperband tuning algorithm, the tuning performance is actually similar to the human performance and much better than the random performance. And using this benchmark, we try to compare the add-on and S3D optimizer with many recently proposed optimizers on 6 different tasks, including computer vision, NLP, graph neural network, and reinforcement learning. And based on our comparison, we show there is no strong evidence that the newly proposed optimizers are better than add-on in terms of the tunability. So this opens a new research direction. How can we develop a new optimizer to improve the hyperparameter tuning time? And that will be a important and very practical research we are trying to do next. So in conclusion, in this talk, we first talk about the scalability of the training. We propose algorithms which has been widely used in the companies, and there are actually some room for improvement because our algorithms still have some limitation, and we are trying to improve over that. And the second part, I propose a new evaluation protocol which consider hyperparameter tuning time. So we show all the existing algorithms are actually competitive under this comparison. So this opens a new direction on developing new algorithms to improve this tunability criteria. Okay, this is the end of my talk. Thank you very much.